Thank you, Dialogue, and for inviting me here to speak. Very honored, especially on the 50th anniversary. So today I'm going to be talking about how I won the programming contest in the general computing category. And yeah, just a little bit about me. I'm 19 years old. I'm in my second year in college, and I've interned with the Carlisle Group for a few years, a few summers. So I'd like to thank Paul Mansour also for introducing me to this competition in APL. So the first part of the problem, it was phase one, which phase one was 1/3 of the judging criteria, and phase two was counted for 2/3 of it. And in phase one, we had to come up with 10 solutions, and our code had to be in one line of code, and they were fairly easy problems. I'll just show one of them just to get into it. So this was the one problem, shorter ones to the front. Write a direct function that takes a vector of vectors as its right argument and returns it sorted by the length of each element. So this is what the problem asks for, with strings, integers, and so my solution was just at the top, the first line up there. Tally everything in the right argument, then just grade up by that and use those indices into the right argument. So I don't think it's one-liner Wednesday material, but it was pretty terse, so I liked it. So now getting into phase two, the problems are going to get harder and as it goes on, so the first ones are pretty trivial. So this is Teeko. This was the first problem, and you might be wondering what in the world Teeko is. And it's a game invented by the magician John Scarney in 1937, and he refined it in the 60s. So the name comes from a combination of tic-tac-toe, chess, checkers, and bingo. And actually, he loved it so much he named his son after the game, which is unfortunate for him, I guess. But essentially how the game works, you have 25 unoccupied spaces on the board. You have two players, and the pieces are called markers. So you'd have the player with the black markers and the player with the red markers, and the black player would go first, and then the red one, and so on until they each play their 4 pieces. So once they could place it on any unoccupied space in the board, and once they have placed all 4 of their pieces, that's when the drop has finished. And generally there isn't a winner after the drop. Then they go on. The black one would move first, and the red one to any adjacent location that's unoccupied until you have a winner, and a winner is defined as being either a horizontal line, vertical line, diagonal line, or a square of 4 adjacent spaces. So for the problem, well, this could easily be represented in APL as a 5x5 matrix using the jot symbol to represent unoccupied spaces, B, the character B for black, and R for red. You could use anything you want, but for this example and the problem, we're using that notation. So we had to come up with a function called winner, which takes the right argument of the 5x5 character matrix representing a Teeko board, and if there's a winner, you would return the appropriate character for the winner. Otherwise, return the character representing an unoccupied space. So using the board defined above, in the previous example, you could see that B was the winner. You could see it's in 4 adjacent, it's a square of 4 adjacent spaces. So what I did was I just collect the unique characters in the right argument, which would be B, R, and the jot symbol. Board's the right argument. And I find the total number of character occurrences on the board. So it's always going to be 17, 4, and 4, maybe not in that order, because you'd have 4 occurrences of B, 4 occurrences of R, and then 4 plus 4, 8. And 25 minus 8 is 17, so the max number is always going to be the character representing an unoccupied space. So using that information, we collect I just call it filler, but that's the unoccupied space. and I don't need to do any analysis on that, so I get rid of it from V. And now I'm going to perform a series of checks, horizontal, vertical, diagonal, and if it's a square. So a lot of these checks are similar, so I'll just show an example of a vertical check. So let's say our right argument looked like this. This is what the board looks like. And as you can see, we have a vertical line of R, 4 R's in a vertical line, so that's going to be the winner. So what I do is I get the right argument in board, which is going to give me a matrix, and once you represent it as a Boolean matrix, the problem becomes very easy. So what I do is I sum each column. I don't do rows. For horizontal lines, I would use rows, but so I sum each column, I look for a 4, sum that up, and that's going to give me my, and then I do this for each element in V, so I do this on B and R. This is the result for R, so it would actually have 2 elements in it, 1 and 0. And then now I just sum up my checks, and I apply that, reduce it on V, which is going to give me R, and I concatenate filler to the front of it. I didn't want to do it at the end because I didn't want to use the parentheses, so I just reverse the string, and then I always pick the first element. So if there's no winner present, it's going to always pick the unoccupied space, so that's the reason for that. So R is the winner. Now moving on to the next problem, it's the ChiSquare test of independence. So a ChiSquare test for independence is applied when you have 2 categorical variables from a single population. It is used to determine whether there is a significant association between the 2 variables. So here's the formula for calculating the test statistic. And as you can see, we can't calculate the test statistic until we have the expected values. So the first task is to calculate the expected values. And this is the formula for that. I'll get into so we have to write an APL function named expected, which takes a right argument of a numeric matrix of counts and returns a numeric matrix of expected values. So let's say this was the data we're given, or this is a table with the we've tallied on the last row and last column. We have tallies, and we want to return a table that looks like this. So the formula would go, this is what the formula looks like. Number for the first box, 2.6053, we come up with that by using this simple expression. And the obvious thing to do here would just to write a loop and calculate each individual cell, but I know that's basically a sin here at Dyalog to use a loop, so I didn't do that. It would be boring. So this is my function. I noticed a pattern in the function, so I just used, I'll show you what it does. Let's say we are given counts, the following counts, and what I do is I tally the columns, tally the rows, and get the shape, get the number of rows and columns. And now I'm going to expand these out. So now they're the same length, x and y, and now I can just apply a simple expression to them and calculate the values. So this is what I do. This is what the formula looks like. We get the tally, the total number of the sum of everything in counts, which is 38, and we're going to divide by that at the end, x times y, and we want to make sure it's the same shape as the matrix we were given. So when we apply this, we get the following answer. So those are the expected values. And now we want to find the chi-square test statistic using that. And once we have the expected values, it's very simple to get it. We just do observed minus expected squared divided by expected. So there's my function. And the next problem we have, this is the third and final problem, we have the matched drugs problem. So for this problem, imagine that you work in the pharmaceutical industry and your company has a database which consists of a list of normalized drug names. Your company also collects information from physicians regarding the drugs they are prescribing, and ideally all the names in that list from physicians would be found in the database of normalized names. However, data entry errors can occur, or the physician's office may enter additional unnecessary information. For example, dosage amounts in addition to the drug name. And so there's going to be a large number of entries that do not match exactly. The mismatched names need to be analyzed and matched, if possible, with database names. Identifying and correcting the mismatches by hand is a costly process, so we've been tasked with automating as much of the process as possible. So this is what function they want. It's you take a right argument representing the list of physician inputs, and the left argument representing the list of database drug names, and you return an integer vector where each element is an index in the list of drug names representing the best match for the corresponding elements in the list of inputs. So a simple example would be you have D representing a database, aspirin, and so on, and I would be a list of inputs by the physician, and you could see some of them have errors. Penicillin's missing an L. Aspirin, it has this unnecessary information. And you want to return the location of the correct match. So D match drugs I, let's say we want to take the first input, aspirin, and the answer would be in position 3, the database. No, penicillin would be the first one, and that's in position 3, and so on and so forth. So this is just a small scale example, but the problem we were working with was much larger than this. We had 2,729 drug names and 4,400 inputs. So as you can see, it's going to get large quickly because the amount of comparisons you have. You'd have to do 12 million comparisons, and with an edit distance function, it depends on how efficient that is, but that could take a while. But really, 12 million isn't a lot in computers, but still, you'd want to eliminate as many possibilities as possible. So just looking at, I'm going to kick it back to the session so I could show you the database. So my idea was to try to eliminate as many items in the database before I apply my edit distance function. So we have a database, just normalized drug names, and the physician inputs we want to correctly map in the database. So I'm just going to show you a little bit of the function. I'm going to trace through a little bit, and I have a stop in there, so okay. So what I'm doing is creating a narrow database. So first, oh, yep.
Increase the font size, please.
Thanks.
Change the colors.
Was 24 good or higher?
Can you switch to a standard color scheme because it's actually completely unreadable?
Oh, really?
Yeah, it's completely
Under options, color.
Yeah. I don't know. Autumn's fitting, I guess. Okay. There we go. So what I do is the current input we're working with is addl@cc, and we want to map that in database and find the correct position. And you could see we want this to map to addl@, just without the cc. So what I do earlier in my function is I get we'll seize the current input we're on, and I narrow it down to figure out I look for breaking point stuff in the string, and I don't work on the whole input. And what I do is I jot dot membership of drugs, and I really check I check for how many similar letters A has with each item in the database. So this is going to give me 6 rows and 2,729 columns. Each column is going to be each item in the database, and 6, the number of rows, corresponds to how many letters are in A. So the shape of A is 6. So I assign this, and see, you could see this is how many letters they share, how many letters they have in common. And now I create a new database, a narrow database, using this information. So like, if you had the string ABC and the string XYZ, you know right off the bat there's no way they're going to be similar. So you could eliminate that from the database before you run any functions on it. So that's what I'm doing here. I look for a 2/3 similarity, and that's what I'm doing in line 17. Oh, I shouldn't have executed. So now our database is only 500 and only has 543 items. So we eliminated 80% of it in this one expression, and it would be much easier now to run our edit distance function on this instead of having the full, 2,729 items in it, and doing this for each iteration. It really helps save some time. And you want to compromise speed and accuracy here, so ideally you want to look, the more items you could eliminate in the database, the better, but you don't want to go too far and eliminate too many, or you might run into problems. But with 2/3, I found that I didn't have any problems on this data set. So now I'll just get the edit distances. And I didn't use any conventional edit distance functions. I just wrote an intuitive one, but I know there are some good ones out there. And so now we have a list in the narrow database, and I find the lowest number in that list, and I have it there. So you could ignore the 0. I'm going to drop that. And so 37. So the item in the 37th. Oh, wait, not in our database, sorry. We have to index into database because they're two different the narrow database and the database are two separate databases. So now we and we do this and we return the location that we need to index into. And you can see it correctly maps to Adalat when we had Adalat CC. So I'll just run this on, I'll just run it on maybe 40 inputs and just show you them side by side with what my function does. Okay, I'll just display this. Oh, need to get rid of that. So on the left you have well, actually no, on the right are the inputs. Let me reverse this, it'll just be easier to see. Okay, so on the left you have the inputs given, and on the right you have what the function returns as the correct item mapped in the database. So you could see Tylenol, and it gets rid of some unnecessary information and it normalizes the names. So that was the third and final function in the problem. And I guess I could take questions now.
So did you solve the problem first and then go back and apply your technique of reducing the number?
Yes. First I did every single possibility, the 12 million possibilities, and it didn't work out too good. And I realized I was just looking at the database, just on a human level. Like if you were comparing each item, right off the bat, you'd eliminate so many elements, and I figured out, well, I should get my program to do that also. So I figured doing that for each item, each iteration would save a lot of time, and it did. So, but at first, yes, I did every single possibility.
How long time in total do you figure that you've spent solving the problems in phase 2?
Well, in total, well, there were 3 phase 2 problems, and they got harder and harder. The first problem, I would say, less than 2 hours for the first one. I mean, they took longer. I mean, this problem, I completed it first, but then I had to go back and revise it, so that does take longer. I can't give you an exact number of hours or
No,
anything.
just a ballpark for problem 2.
Problem 2?
3.
Okay, let's see. I didn't log this down, but problem 2, I would say, just finding out the pattern was the hard part in the ChiSquare function. And then there was 2 tasks. The second one was easy, instantaneous once you figure out it's just applying the formula for the test statistic, but the expected values took longer. I would say, 2 hours, 3 hours.
And the last one?
That one took a little longer. I would probably a couple days, just on and off working on it,
One more question. Having been an intern in Carlyle Group, you obviously already had quite a good insight into the APL programming language, so I assume that this was not your first encounter with Dyalog APL.
No, it hasn't been. And actually, I did the competition last year. I came in second place, so now I finally got the first place. I wasn't stopping. I got it. And then, yeah, I've done work at the Carlyle Group with, and also Steve Mansour. He's over here in the audience. I've worked with him a little bit too at the Carlyle Group. So yeah, I've worked with APL before.
Thank you. That leads a bit to my question. I was going to ask, besides the technical issues, could you tell us a bit about your background and why this contest appealed to you, and what you got from it, and what advice perhaps you might have for us APLers? And before you answer, I just want to point out something. You've just solved a major problem that I have on my desk right now. or you've led me to a solution. I have a word matching issue in my day job right now that I have to work with, so this solves it. So go ahead. Thanks.
Okay. Was the first part of your question was just...
Tell us about your background. Why is this
okay.
to you?
Yeah. At the Carlyle Group, Paul Mansour, the president of the Carlyle Group, introduced me to the competition and encouraged me to do it. And I really like doing it because it really does help you apply your APL skills. When you're given a problem, that's when you really have to. It's one thing to just read about it and know it, but when you actually have to practice exercises, like, in math problems, you have to really do the homework and do the problems to get and understand the concept of them and figure out how the primitives work, operators, and everything. So that's what I really enjoy about the competition. You do learn a lot coming out of it. You learn that John Scarney named his son after his board game, Teeko.
So, from your perspective, where do we stand in the APL world? Are we headed in the right direction? What do we
Yeah,
have
I
to
would
learn?
say you're headed in the right direction. And there's a lot of work being done here. I mean, I'm just looking at the presentations. It's just a constant upgrades and modification, which is really good, staying current.
Okay. Thank you very much. Congratulations.
Thank you. Thanks.